Hello and welcome back to the Stiffness Method series. We've already covered the basic concepts and we've already developed the stiffness matrix in local coordinates for a bar element. Today we will focus on deriving and coding the stiffness matrix for a beam element in its own local coordinates. By the end of this session, you'll not only know how to fully derive the matrix for a beam element, but also how to code it so you can use it again and again for any beam element. So we've already discussed the basic concepts that we need to start implementing the stiffness method. We've already developed the stiffness matrix for a bar or truss element in its local coordinates, and so now we'll move on to developing the stiffness matrix for a beam element in its own local coordinates. We'll start by developing a stiffness matrix for a beam element that includes axial forces, shear, and moment. To derive the Euler-Bernoulli beam element stiffness matrix, a number of assumptions are made. These assumptions will simplify the behavior of the beam and allow for a simpler analytical solution. The assumptions for the Euler-Bernoulli beam theory are the material is linearly elastic and isotropic, and that means that Hooke's law applies and the material properties are the same in all directions. We'll be dealing with small displacements and rotations, and that means that the geometry changes do not significantly affect equilibrium. We also have the key assumption that plane sections remain plane and perpendicular to the neutral axis. This is the main thing that defines an Euler-Bernoulli beam. Shear deformation is neglected, and that makes this formulation best for slender beams. There's no axial bending coupling in local coordinates, and that means that axial and bending effects remain independent, and we'll see that as we develop the matrix. The cross-section is constant along the length, so we're working with prismatic beams. And the last assumption is that each element has two nodes, and in 2D, each node will then have 3 degrees of freedom: the axial displacement, the transverse displacement, and rotation. So now that we've established those assumptions, we can look at our beam element. We can see it's got 2 nodes. At each node, there are 3 degrees of freedom: an axial displacement along the local x-axis, a transverse displacement along the local y-axis, and a rotation around the z-axis, which, as you know in 2D, acts out of plane. This gives us 6 degrees of freedom in total for this element, and these are the fundamental variables that we need to use to describe its behavior and construct the stiffness matrix. At node 1, we label the degrees of freedom as u1, v1, and θ1. At node 2, similarly, they're u2, v2, and θ2. Here, u represents axial displacement along the local x-axis, v represents the transverse or vertical displacement along the local y-axis, θ represents rotation around the z-axis, which is perpendicular to the plane, and when we assemble the stiffness matrix, it will relate all nodal forces and moments to these 6 displacements and rotations. As we saw previously, the stiffness matrix size depends on the number of degrees of freedom. We've already seen here that in a beam element there's 6 degrees of freedom, and therefore the stiffness matrix will be a 6 by 6 matrix. Each member of the stiffness matrix is defined as the member stiffness influence coefficient. As you recall, to derive the stiffness matrix, we use the direct stiffness method approach. We apply a unit displacement or rotation at 1 degree of freedom, we restrain all other degrees of freedom, and then we calculate the resulting forces and moments at every degree of freedom. The forces and moments generated from this single unit displacement form one column of the stiffness matrix. By repeating this for each of the 6 degrees of freedom in turn, we construct the full 6 by 6 matrix for the beam element. As we'll find out when we develop these stiffness coefficients, the stiffness matrix is symmetric. This is because our material is linearly elastic and the beam is under small displacements. And that means that the work done by one set of forces acting through the displacements caused by another set of forces is equal to the reverse situation. This is called Maxwell-Betti's reciprocal theorem, also known as Maxwell's reciprocal theorem. The theorem states that for any linear elastic structure in equilibrium, the displacement u1, which is the displacement at point 1 in the direction of a unit load applied at point 2, is equal to the displacement at point 2 in the direction of the same unit load applied at point 1 U21. This directly translates to the member stiffness coefficients being reciprocal, and we'll easily prove this as we will shortly show. And this, in turn, means that the stiffness matrix is symmetric. This is very useful because it means that we only need to calculate half of the coefficients directly. The other half are automatically known. For example, once we know how a vertical displacement at node 1 produces a moment at node 2, we also know how a unit rotation at node 2 produces a shear force at node 1. We'll now begin deriving these terms for the degrees of freedom in our beam. Let's start off with axial displacement, which we are already familiar with. We'll hold all degrees of freedom apart from degree of freedom u1. At u1, we give a unit displacement of 1 and then hold in place. In linear elastic small deformation theory, the assumption that we're working with in the stiffness method, axial strain depends only on the axial displacement difference between the two ends. Similarly, bending strain or curvature depends only on rotations and transverse deflections, not on axial stretch. This means that in a beam, axial loads aren't coupled with bending because the stretching of the beam along its length and the bending curvature act independently under small deflections. And this means that the axial terms are independent from the bending and shear terms. We'll shortly see what this looks like in the stiffness matrix, but already here we can see that any terms that are not in the axial direction are zero. However, a reaction will develop at degree of freedom u2, just as we've previously seen in the bar. So K41 is going to be minus EA over L times U1, and as U1 is 1, we end up with minus EA over L. And then using simple equilibrium, we can find that K11 equals EA over L. Once we've done that, we can apply a unit load at degree of freedom U2. So in this case, U2 equals 1, and all other degrees of freedom equal 0. This displacement produces an axial reaction at degree of freedom U1. So U14 equals minus EA over L times U2, which is 1. So we end up with minus EA over L. Using equilibrium once again, we can get that K44 equals EA over L, and all other reactions are 0. So for in this case, the fourth column of the stiffness matrix contains only two non-zero coefficients, K14 and K44. And together with a previous slide, this completes the axial block of the stiffness matrix. Notice again how the axial stiffness is uncoupled from bending and only degrees of freedom U1 and U2 are involved. So, looking at the two cases we just considered, from the axial displacement at degree of freedom 1, we found K11 and K41, and for the axial displacement at node 2, we found K14 and K44. All other coefficients, as we've already established in those two columns, are 0. So at this stage, we know the stiffness coefficients that connect the axial displacements at node 1 and 2 with the axial forces at those same nodes. Using reciprocity, K14 equals K41. This is what we've already shown in our calculations, so we've kind of shown Betti-Maxwell's theorem here. To complete the axial part of the stiffness matrix, we can now identify all the remaining coefficients in the first and fourth columns and rows. Because we've already established that in small deformation linear elastic theory, the axial displacement is independent of bending and shear, there is no coupling between the axial degrees of freedom and the vertical displacements or rotations. And that means that all the values relating to the vertical and rotational degrees of freedom have to be 0. We can show this using Maxwell-Betti's theorem, or we can show this just by establishing that they are in the bending and shear directions. So the only non-zero values in the first and the fourth columns are the axial stiffness coefficients that we derived earlier for K11, K14, K41, and K44. All the other entries will be 0. And if we put this on the stiffness matrix, we can show all the coefficients associated with the axial displacements at degrees of freedom U1 and U2. The axial block is now finished, and we can move on to the shear and bending contributions. To find the next set of terms in the stiffness matrix, we need to give a unit displacement in the direction of V1. That means a vertical displacement at node 1, and then we hold it in place, while all the other degrees of freedom are restrained. As you can see, reactions will develop due to this imposed displacement. But this case is much more complicated than the axial one, because it creates an indeterminate structure that we need to solve. To solve it in this lecture, we'll be using the flexibility method. Now, this is a different approach which is covered fully in its own dedicated lectures. Our focus in these lectures are on the stiffness method, so I'm not going to go through the full flexibility derivation, but I'm going to use the principles. These principles all rely on our knowledge of displacements under unit loads, which we will accept here as given. There are many tables that you can use to find these displacements, and also don't worry because I cover displacements in other lectures. So, if you don't get this flexibility method, you can look at the dedicated lectures, but don't worry too much because that doesn't influence what we understand on the stiffness method. And one final reminder before we move on, the axial terms in directions u1 and u2 are uncoupled from the bending, and that means that the coefficients k12, k42 are 0 in this case. So for this displacement pattern, our job is to determine the non-zero terms in the second column, k22, k32, k52, and k62. When we apply a vertical displacement, v1, the resulting reaction problem is statically indeterminate. So we cannot determine all the reactions just using equilibrium. As I mentioned, we're going to use the flexibility method to deal with this. And this is the process. We start off with a primary structure, which is the beam made statically determinate by removing the redundant forces, or the forces we're solving for. We apply unit loads one at a time in the directions of the redundants. For each unit load, we calculate the corresponding deflections and rotations at those redundants. These calculated displacements are called the flexibility coefficients. And once again, I want to be very clear. We're not doing the full flexibility derivation here. That is covered in its own lectures. Our focus here is the stiffness method, so we are just going to use the flexibility method results, so the known deflections under unit loads, in order to complete the derivation. Flexibility is our supporting tool here to help us move forward. To apply the flexibility method, the first step is to set up the primary structure. This is a determinate and stable structure. To do that, we need to discover first how many times the structure is indeterminate. In this case, this is a twofold indeterminate structure, which means that we need to select two redundants, two extra unknown reactions that prevent us solving the problem directly with equilibrium. So what do? We temporarily move those redundants, creating a primary structure that is statically determinate. Once we have the determinate primary structure, we apply unit loads one at a time in the directions of the removed redundants. We can then calculate the deflections and rotations at those locations under each unit load. And we can then use those results to solve the system for the unknown redundant reactions in the original system. Now that we've defined the primary structure, that cantilever beam, the next step is to apply unit loads one at a time in the directions of the redundant. For each unit load, the force at node 1 and the moment at load 1, we can calculate the resulting deflections and rotations at the redundant locations. These tell us how the structure responds to the loads. Once we know the values, we can determine the redundant reactions that must exist in the original system. So here we're just going to use that flexibility principle. We've applied a unit load at node 1 and a unit moment at load 1, and I've taken from deflection tables the displacement and the rotation for each of these cases. Now that we have those units, deflections, and rotations, the next thing we need to do is write compatibility equations. Compatibility means that the displacements and rotations in the real indeterminate structure must be consistent with the imposed displacement pattern. The supports and connections don't allow arbitrary movement. Everything has to fit together correctly. So here's what that means in practice for us. In terms of displacements, the displacements that we got from applying that unit displacement at node 1, plus the displacements applied by the redundant reactions, must equal the actual displacement at the location in the real structure. In our case, that displacement is 1. So in other words, the total deflection at each of the redundant locations is the sum of the contributions from the imposed unit displacement and from the redundants. They must match the total values. So as you can see in equation 2, the rotations will equal 0, because in fact we just moved node 1 up vertically, we did not rotate it, and we held it in place from rotation. By solving these compatibility equations, we can now determine the redundant reactions, and once we know those, we can substitute them back into the structure to get the stiffness coefficients. On this slide, I've just introduced the values for the deflections and rotations into the equations that we set up on the previous slide, and I've just simplified them a bit to make solving them simpler. In the previous slide, we simplified our two simultaneous equations and isolated R32 in equation 2. I'm just going to substitute that back into equation 1, and that leaves us with one unknown in a single equation, which we can solve directly. And once we have that, we back substitute to find the value of the other redundant. So really, this is just a simple process of rearranging and substitution, exactly like solving any pair of simultaneous equations. The end result is that now we have the numerical values for both redundants, and we can use them on the next slide to find the other unknowns. With the redundant reactions now known from the compatibility equations, we can go back to the structure and just use equilibrium to determine all the other reactions. We already know the redundants, so just by applying a sum of forces in y and a sum of moments, we can calculate the remaining shear forces and bending moments at node 2. And once we've done that, all the reactions for the displacement pattern v1 equals 1 are fully determined. Since all our solutions just included unit displacements, the reactions we've found are actually themselves the stiffness coefficients by definition. So directly, R22 is K22, R32 is K32, R52 is K52, and R62 is K62. So once we substitute all the values we found, we know that K22 is 12 EI over L cubed, K32 6 EI over L squared, 52 is minus 12 EI over L cubed, and K62 is 6 EI over L squared. So now column 2 of the stiffness matrix is complete. Placing all of these results directly in the stiffness matrix fills up column 2. Using symmetry, we can also fill in all of row 2. And this means that at this stage, we have filled in all the terms associated with a unit vertical displacement at node 1. Next, we'll move on to the case of a unit rotation at node 1, theta 1. That means that theta 1 equals 1, whereas u1, v1, u2, v2, theta 2 are all 0. Applying this displacement pattern means that we rotate node 1 while keeping everything else fixed. This introduces bending into the element. Just like in the vertical displacement, the structure is statically indeterminate, so once again we need to rely on compatibility. The principle will be exactly the same. The rotation produces reactions at the restrained degrees of freedom. Applying compatibility and equilibrium, we solve for those reactions, and because we applied a unit rotation, the reactions directly give us the stiffness coefficients in column 3. Over the next few slides, we'll go step by step through this to determine the terms. Rotating node 1 while holding the rest fixed creates a system that cannot be solved just using equilibrium. To do that, once again, we will use the flexibility method. We'll form the primary structure by removing the appropriate redundants and make the system statically determinate and stable. Once we have this primary structure, as we do here, this cantilever, the steps are the same as before. We'll apply unit loads at the redundant locations, calculate the displacements and rotations, solve using compatibility equations, and then get the redundant reactions for the rotation case. Once again, our primary structure is a cantilever, meaning that at node 1 we removed the vertical reaction and the moment reaction. So we need to apply unit loads in those two directions. So you can see here on the left a unit force in the direction of the reaction force at node 1, and on my right the primary structure with a unit moment at the location where we took the moment off and created that redundant force. Each of these unit loads produces deflections and rotations at the redundants. So at this stage we need to identify how the structure responds, and here once again I've found the values for the deflection and for the rotation. These unit load deflections and rotations feed directly into the compatibility equations on the next slide. In this slide, we'll set up the compatibility equations. This means that the imposed displacement pattern must match the total displacements in the structure. In this case here, the unit rotation θ1 at node 1 produces certain displacements and rotations. The redundant reactions also produce displacement and rotations at the same locations. And the sum of these two must equal the imposed values from our displacement pattern. Since the beam was rotated and held in place, there are no vertical displacements in the real structure, and therefore the vertical displacements must equal 0 for equation 1. The rotation is 1, so the sum of rotations from both the redundants have to equal 1, as we can see in equation 2. Once again, I've just written out the equations from the last slide and just rearranged them and put in the actual displacements that we got from the unit force and the unit moment. In this slide, we simply take the two equations that we've already written and simplified, and we solve the two simultaneous equations. In equation 1, we isolate R33, and then we can substitute it into equation 2. And once we've solved equation 2, we've found R23, and we can substitute back into equation 1 and find R33. So R23 works out as 6EI over L squared, and R33 works out as 4EI over L. So at the end of this step, we now have values for both of the redundant reactions. Now that we know the values for the redundants, we use equilibrium to determine the remaining reactions. So here you can see sum of forces in Y, sum of moments, allow us to calculate the moment and the force at node 2. So this step does not really introduce anything new, simply applying the standard equilibrium equations to complete the set of reactions. Since we applied a unit rotation at θ1, the nodal reactions we just calculated using equilibrium are directly the stiffness coefficients in column 3 for the matrix. And we can just write them out, as you can see on this slide. So we found K23, K33, K53, and K63. So that means that we've managed to fill in column 3 of the stiffness matrix, and using symmetry, we can immediately fill in the corresponding entries in row 3. So at this point, all the terms linked to a unit rotation at node 1, θ1 equals 1, are now determined. So up to now, we've analysed the axial displacements at node 1 and 2, u1 and u2, a vertical displacement at node 1, v1, and a rotation at node 1, θ1. And this gave us columns 1, 2, 3, and 4 of the stiffness matrix, with symmetry filling in the matching rows. We're not finished yet though. We do need to analyse degrees of freedom at node 2, v2, and θ2, the vertical displacement and the rotation. We can start with a vertical displacement at node 2, v2. In this case, it is a mirror image of v1, so we don't really need to go through the full flexibility derivation again. The results follow directly, and we will find K25, K35, K55, and K65. And finally, for the last degree of freedom, the unit rotation at node 2, θ2, here θ2 equals 1, and u1, v1, θ1, u2, and v2 are all 0, and this is the mirror image of θ1 equals 1. So again, the pattern of coefficients carries over. And from here we find the missing K66. So by recognizing the vertical and rotational degrees of freedom at node 2 as mirror images of the ones at node 1, and by utilizing symmetry, we have now filled in columns 5 and 6 of the stiffness matrix. And here, finally, is the complete stiffness matrix for the full beam element in local coordinates. I just want to make a few important observations. Symmetry. So notice how the matrix is symmetric. And this comes directly from Maxwell-Betti's theorem, which tells us that the work done by a force at degree of freedom I under unit displacement at degree of freedom j equals the work done by degree of freedom j under unit displacement at degree of freedom I. We can also see here decoupling of axial and bending. The axial degrees of freedom form their own block with terms EA over L, plus and minus. The bending degrees of freedom that we can find in columns 2, 3, 5, and 6 form another block with terms involving EI. All the coupling terms between the axial and bending are 0, which matches exactly what we expect from linear elastic small deformation theory. And the last thing, units. We need to first remember that the end goal for this is to make sense, right? Force equals the stiffness matrix times displacement. The axial stiffness terms, like EA over L, have units of force per displacement, FL. When we multiply them by an axial displacement L, they'll give us a force, F. Bending stiffness terms, like 12 EI over L to the power of 3, also reduce to force per displacement, and they will also give us a force when multiplied by a displacement L. And the rotational terms, like the 4EI over L, have units of moment per rotation, so force times length divided by radian. When we will multiply them by the rotation in radians, we will get a moment, force times length. Before we move on to coding, I just want to touch on a special case of the beam element, the axially rigid beam, and you might find this as the description for the stiffness matrix in other books. In this case, we assume that the axial forces are negligible and the element's response is governed only by bending moments and shear forces. In other words, the beam cannot stretch or shorten along its axis, and there are no axial displacements or axial forces. This is a reasonable assumption for certain cases, like situations where axial deformations are constrained, like boundary conditions or high axial stiffness. So for the purpose of developing our beam element, we'll assume axial rigidity. The formulation of the element is based on the following assumptions. Material is linearly elastic. Hooke's law holds, stress is proportional to strain, and any material constants are fixed. Small displacements and rotations, linear strain displacement and equilibrium assumptions apply, and the rotations are small. Axial rigidity or no axial deformation, the axial stiffness EA is infinite. And this means that the axial degrees of freedom are excluded. No axial strains or forces are considered. There's a constant cross-section, so this is a prismatic section, and there are again 2 nodes per element. But each of these nodes now have 2 degrees of freedom, a vertical displacement V and rotation theta. The axial degree of freedom is excluded. Compared with the general beam element, we are simply simplifying the formulation by ignoring axial effects, but still retaining bending and shear. We'll start by looking at how the assumption of axial rigidity changes the element degrees of freedom. For the full beam element in 2D, each node had 3 degrees of freedom: axial displacement along the beam's axis, a vertical displacement, and a rotation. When we assume axial rigidity, the axial displacement is removed, and that means it's excluded from the formulation, and that leaves only 2 degrees of freedom, the vertical displacement V and the rotation theta. So across the whole element, we now only have 4 degrees of freedom in total. Since we have 4 degrees of freedom, the immediate consequence is the matrix reduces in size, and instead of a 6x6 matrix, we have a 4x4 matrix. The smaller system makes the formulation simpler, while still capturing the essential bending and shear behavior of the beam. Essentially, we can see that this is the 6x6 full matrix without axial terms. Since they were not coupled with any other terms, this is a really simple step to take. Now that we know the form for the stiffness matrix, the next step is to implement it in code. We'll do this for the full 6x6 matrix, but once you know how to do this, it'll be easy to create the same code for the 4x4 axial rigid stiffness matrix. As we did with the bar element, we will write a short program that takes into account beam properties such as E, I, A, and the length L, and automatically produce the element stiffness matrix. We'll go through an example of how this can be done in MATLAB and Octave. The 2 languages are very similar, so the same code will typically work in both. The program will calculate the individual stiffness coefficients and assemble them into the element stiffness matrix in local coordinates. Later, we'll use these matrices to assemble together to form the global stiffness matrix for the whole structure, and we'll use that for solving displacements and internal forces. So let's begin coding. From here on, we'll be looking at the MATLAB script notation. As we mentioned previously, the percentage in MATLAB means that it's a comment, a non-executable line. We start off with clearing everything, and this means that if we already ran the program and are tweaking it, we will not risk having any variables from previous runs stored. So we clear all the variables, close any open windows, and clear our screen. Each command, as you can see here, ends with a semicolon. So next we need to define the material properties, E, A, I, and L for our single element. We need to be very careful that we're consistent with units. Here we will work in newtons and meters. As you can see here, I've used some arbitrary values, E, which is suitable for steel, and a random cross-section for A and I. You can see here that this is essentially a solid rectangular section of 20 millimeters. Hence the E-6 and the E-12 are organizing my units into meters. I've taken L as 1 meter. Obviously, you can change these to fit whatever element you have in your own code. The next thing I do is define the size of the local beam stiffness and also zero out. So we just reset it to zeros and note that it's a matrix of 6 by 6. Then we enter all the terms that we've discussed for each member stiffness influence coefficient. So you can see here, each member value ends with a comma, each row of the matrix ends with a semicolon, and the whole matrix is bound by these rectangular brackets. Be careful to ensure that you've entered this correctly, as if you mismatch the numbers of members to the original 6 by 6 that we defined, you will get an error. And now that we have that, we can just press on this green arrow to run the program. And now that we ran the program, we can see all the results in the workspace. You can see all the properties we defined like A, I, E, and L, and additionally the code results in the full 6 by 6 matrix for the beam in local coordinates. If we double-click K-beam, the matrix values then pop up. You can see here that copying the exact same script into Octave works and gives exactly the same results. Thank you for joining me in developing and coding the stiffness matrix for a beam element in its local coordinates. Join me next time when we introduce several of these elements into a structural stiffness matrix.